Good afternoon, class. Today we will be discussing about dynamic lateral force procedure on the basis of the code presented by the National Structural Code of the Philippines, uh, 2015. Although the procedure is not different when you use older NSCP codes or even other international codes. So we will be doing a specific computation of the lateral forces on the basis of the NSCP 2015 guideline. Okay. So I'd like to point out that the dynamic lateral force procedure is not really a dynamic analysis in the sense that we are just computing the dynamic forces that we are going to use in a static analysis. So this is actually a pseudodynamic analysis. So it's not a real dynamic analysis in the sense that the time factor is no longer there. No? We are just using an equivalent response spectrum to get the modal uh, participation factors we need for the computation. Okay, so the objective of this analysis is to use different modes instead of using only the fundamental mode. In the static lateral force procedure, we only consider the fundamental period or frequency, while in this RSA method, which is a pseudodynamic analysis, we will be doing modal computations to get the mode shape vectors, okay, and also the modal natural frequencies will be computed and related to the design. Okay, so we have a design spectral graph which is normalized to 1.0 G that we are going to use for the computation of the dynamic forces. Okay, so let's have now a building, a three-story building with an elevation at the longitudinal section consisting of 1, 2, 3, 4, 5, 6 bays, and in the transverse direction consisting of 2 bays. Okay, so we ought to compute for the forces that can be placed horizontally at each floor. Okay, so these are now the unknown forces, F1 or F3, F2, F1, that we need to solve. Okay, of course this building should first be analyzed in terms of the weight, but assuming that all the weights were already computed on the basis of the given analytical model. So we now have here an analytical or mathematical model in the form of a spring mass system. Okay, so what are these three forces here that will represent a dynamic force rather than a static force? Okay, in terms of modal participation factors. So the modal participation factors is actually related to what we have discussed last meeting about the determination of the mode shape matrix and some normalization procedures to see to it that the values will be very pleasing, no, to the eye and to the one using the data for computation. Okay, let's now consider some parameters in the form of the modulus of elasticity, which are of course must be consistent in terms of units. This is in Pascal. Okay, this is in meter, this is in meter, this is in meter per second square, this is in meter. Okay, so our unit is actually consistent in terms of a Newton, meter, and second square format, such that you don't need to worry about conversion later, so you must be able to use a consistent unit, no? That's why in softwares we are to set the limits or the units first prior to modeling. So the weight of each floor is given in terms of W1, W2, and W3. Of course, the moment of inertia is given by this formula BH cube over 12, which will be used in the determination of your story stiffness K on the basis of a 12 EI over L cube formula. Okay. So for simplicity again of computation, let us assume that all the columns are uniform in terms of the dimension at each story, so that the total stiffness on one story will simply be equal to the number of columns, which is 7 by 3, 21. Okay, so we have all in all 21 columns. Okay, so we are solving or analyzing the whole frame, and we are actually computing F1, F2, F3 based on the whole weight of the building. So the differential equation of motion is readily obtained by knowing the DEM and the form of your stiffness matrix. I have already shown you that this can be easily assembled by connectivity principle. Okay, so this is a typical three-story shear building model. So it's just a K1, K2, K1, K2, K3, K3, then negative K2, negative K3 symmetric. So you know, and the mass is always a diagonal matrix in the form from M1, M2, M3. Okay. So again, the units are in kilogram, Newton, meter, Pascal, and seconds. Okay, so Pascal, Newton, meter, second, and kilogram. Okay, so kilogram will be obtained by dividing the force with the G. Okay, so you get a Newt Newton second square per meter is equal to 1 kilogram. Okay, so take note of that. Okay, so 1 kilogram is equal to 1 Newton second square over meter. Okay, let's solve the eigenvalue problem, but this time I don't want to use any longer the long method. So there are a lot of software that can solve for the eigenvalues and the eigenvectors by simply plugging in the K matrix and the mass matrix. Okay, so the mass matrix is simply the weight divided by the G. Okay, so this is converted into 10 to the 3 because I think your given value here for the weight are in kilonewton. Okay, by the way, this weight is in kilonewton, so we have to convert it to newton by multiplying it to 1000, okay, before dividing it with G. Okay, so these are the two formula or function. It's a built-in function in MathCAD that you can use to solve for your eigenvalues and your eigenvectors. But I'd like you to be careful that the eigenvalues for omega squared, okay, so these are your omega 1, sorry, these are your omega I squared, okay, and these are your phi ij are arranged, or sorry, are not arranged in order of increasing frequency. So if you'll notice, it's the other way around, no? So your fundamental must be on top and your last mode must be at the bottom. Okay, so if you reverse this to be your Wi, okay, so if this is your W1 square and this is your W2, this must be your W3 square. Okay, so it must be in the order of increasing frequencies, so you have to jumble them. Okay, for your eigenvectors, this must be your first vector phi1, and this must be your first vector phi2, second vector I mean, and this must be your third vector phi3. So take note that you have to arrange it in an order later, okay, so as to be consistent in your computation. And perhaps you are wondering why these are all negative. So don't worry the sign, for as long as this is one-sided, okay, two mass on one side, one mass on the other, and one mass, two mass on the other side, and the middle mass is on the other side. Okay, so it's just like taking note of what I have drawn in the previous lecture, that this is the first mode, okay, and then you have here a second mode in this form, okay, and the third mode can be going here. So let's choose another color, choose blue color, okay. So the third mode can be here, and then can be there, then it can be there. Okay, so did you get the point? So this is all in one side. The two sides are on one side. Okay, the other on the other side, and the two sides on one side, the middle on the other side. Okay, so these are the three modes of vibration. This is now your phi 3, then the green one is your phi 2, and then the red one is your phi 1. Okay, so that is how you don't worry about the sign. For as long as it's consistent, this can be positive, 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 negative. This can be negative, positive, negative. Okay, doesn't mean anything. Do not change the values later. Okay, they are just shapes to serve as guide. But we need to arrange it before proceeding with the computation. Okay, so this is a way on how to arrange it. I will not explain to you because this is a MathCAD language. So I have arranged it in an order wherein okay, my omega squared becomes increasingly uh, arranged arranged in an increasing manner in terms of the squared of omega. Okay, so then I just switch on the first vector, I put it on the last, the third vector, I put it on the first, and the middle vector is just the middle, the same. Okay, so this is now your eigenvector phi1, eigenvector phi2, and eigenvector phi of 3. Okay, so this is now my step to arrange it. If you don't want to use a MathCAD, you can arrange it manually. Okay, so this is the arrangement process. Okay, let's now try to normalize. Again, so we normalize the mode shape by using the phi matrix and dividing it with the denominator, which is square root of phi1 transpose m phi1. So these are now the normalized normalization factor or denominator. These are now for D2 and then for D3. So we make use of the normalized vector in terms of phi1n, phi2n, and phi3n by dividing it with D1, D2, and D3. So we get this as your normalized mode shape vectors. Okay, so again, you can use a positive sign here, consistent. You can use a plus plus minus here, and you can use a plus minus plus. It doesn't matter, no? You can mix them up. So your phi and matrix now is an assembly of these matrices in this form. So 39, 69, 85, 84, 30, 73, and 63, 82, 45. Of course, with the sign. Multiplied by 10 to the negative 5. So that's your phi n matrix. So the equivalent matrices now can be checked in the form of the phi, pm, phi. What do you call this? Orthogonality procedure. Okay, so remember we are using the property of orthogonality to check whether your matrix will be converted into an identity matrix almost, okay, and a diagonal matrix, assuming that the values here are almost zero compared to the square of the frequencies. Okay, so these are now the natural frequency square. So that's a way to check. We are actually checking it. So if you are using a software, you might as well check it. So again, the advantage of viewing a normalized mode shape matrix is that equivalent matrices will yield almost these values. And for the determination of the modal participation factor, which is will be used on the computation of your forces later, so it is the same as a normalization procedure. Okay, so you just have a phi tm identity is equal to phi all over phi tm phi. Okay, so you are just trying to to obtain a factor that will normalize, okay, your equation into an identity or an orthogonal equation, and these are the factors obtained from the first vector, the second vector, and the third vector. So we have here values, and again the sign are not that important, because later on the sign will just be squared, and therefore your value will still be positive. Okay, so ignoring the sign, we have now your, we call this the modal participation factors. Okay, in percentage you can get it 71.9, 20.21 all over 7.88, which means to say that your first degree of freedom here, or your mass here, contributes 71% in as far as your uh, uh, the effect of the distribution of your modes is concerned. Okay, that's why sometimes this is called the modal mass participation factor. Okay, so for mass 2, it simply means that 20.21%, which is less than, of course, 71.9, is participated by mass 2 in as far as all the modes are concerned. Okay, and so on and so forth. Of course, the third mass participation factor is very small, since your mass at the top is smaller than the mass at the first and the second. Okay, so after solving for this modal participation factor, we determine the spectral acceleration normalized to 1.0 g using any code. This time we will be using NSCP 2015. And remember that our value for omega, not omega squared, are the following. So these are the omega 1, omega 2, omega 3, increasing frequency, 16.83, 46.61, and 66.182. So these are now the the frequencies that we will convert later into period t to solve, okay, your equivalent lateral forces using the response spectral graph. But before we can use the response spectral graph, we need to uh, first to understand the seismic parameters, which I will be discussing on the next video, uh, before we continue solving this problem related to dynamic lateral force determination. Okay, so I'll see you on the next video.